Hey, g'day, it's Prezza here. Thanks for joining me in the shop today. Today's project is to build a collet rack that goes on the side of this somewhat benevolent Bridgeport milling machine that came into my life this year. Now, I've done a number of upgrades on this machine already. I stripped and rebuilt it, I refurbished the paint, and it's getting to the point now where I want to be able to use the machine regularly, and that means having ready access to the R8 tooling that goes in the spindle. Now, my old milling machine was all Morse taper tooling. Still got all of that, and it basically filled up all of the drawers in my rolling tool cabinet, but I do want to be able to access any tools that I need from the front of the machine without having to walk around and get it out of the drawers. So let's take a look at how that rack might work. Now, this is the area where I want this collet rack to fit against the side of the Bridgeport column. Now, you can buy these, they're commercially available as a die casting, and they have a pair of lugs that are screwed to the side of the column and a flat surface on top which holds R8 tooling. So it's got a number of holes bored in it, got some slots for spanners and other accessories as well. Now, I figured I could replicate this using a pair of castings as the brackets and then a flat surface on top, which I'm going to make from some sheet material. Now, you're probably saying, well, why don't you just buy one? Well, I could, but this is half the fun of these workshop projects, is being able to do it yourself. Now, these castings are fairly straightforward in that they just have two mounting surfaces, and we just need a pair of holes screwed or drilled through this leg of the bracket here, another pair drilled through here, and I need to be able to machine the top face of the bracket and this surface here. Now, on the face of it, that seems fairly straightforward. One of the challenges with making castings is that you have to be able to withdraw the pattern that made this casting from the sand mold. And what that means is you need to have some draft angle. Now, on this surface of the casting here, that's tapered. And if it were not tapered, it would be very hard to remove this from the sand mold without breaking it. Now, that in itself creates a problem too, that to get the draft angle consistent on both faces, the front and the back, it means that this angle here between the top of the bracket and this face here is no longer 90 degrees. And one of the things that I need to be able to do here is to machine this surface, so not only is it the correct radius, but it also has to be square to this face here. This illustrates the problem that we have here. This back face, which is the curved face that fits against the Bridgeport column, is not square to the top face, and that's just a function of making castings. So machining this back face here is non-negotiable. It has to be done, and the challenge is, how do we do that, and how do we maintain the correct radius on the back face of that casting net? In case you're wondering how I got the diameter of the column at this point, I've had this pair of calipers for ages and I don't think I've ever used them. And when I was looking at trying to replicate the castings to match that curvature, I got these calipers out and I measured the top of the column there. As it turns out, it's 15.5 inches diameter, around about 394 millimeters. But remember, this surface here is not machined, it's just as cast and it's been filled and painted. So when I was working out my casting patterns, I got as close as I could, but it's not going to be perfect. My starting point when I do a project like this is always to model the three-dimensional parts and then create some 2D drawings. Now, this drawing here shows the machined casting, not as it is at present. So it includes the correct 90-degree relationship between the top of the casting and the side of the casting. And I've got some hole centers marked out here, and I'm going to do all of that first before we begin any machining. Now that we have that surface there machined flat, and that will be the top of the bracket at a later stage, we can turn our attention to machining this circular face here. Now, I won't lie to you, I've already had a go. And here's one I did earlier. Now, this has been done as a 3D machining process on my little CNC milling machine. And most people who are competent CNC machinists will look at that and say, gee, that's basic. And I agree, yeah, it's a very, very basic machining process. Now, I'm no stranger to CNC machining. I did a very steep learning curve on this process back in the early 2000s. I was involved in a program called F1 in Schools, and we had access to a 3-axis Denford CNC router. And I was thrown in the deep end, had to learn how to do 4-axis machining, or at least 4-sided machining on this little CNC router, and we ended up setting up some very sophisticated tool parts on that little machine. But here at the home shop, I don't get too involved in really complex CNC machining. Most of what I do is 2D or 2.5D. This is actually the first 3D machining process I've done in this mill. And I know it looks a bit rough and ready, but this is all going to be up against the column in the mill and you won't see it. I can grind that flat if I need to. And yes, I could probably get a much smoother finish on that with smaller step overs, but at the end of the day, it's not worth it. Nobody's ever going to see it. So just to give you some idea of what we're up against here, I've drawn out the geometry of what we're trying to achieve here. Now, each one of these brackets needs to sit against this 394 diameter circle, and the edges, the inside edges, need to be 180 millimeters apart. So we're looking at something like that. And of course, this face needs to be dead square to the center line, or dead parallel to the center line of the column. So that's the geometry. Now, if I was going to do this on a manual mill, like a Bridgeport, I'll show you what I had in mind. So here is the layout I would use if I was setting this up on my Bridgeport mill as a manual milling operation. So the first thing we'd need is an M12 stud and a matching T-nut sitting in one of the T-slots on the Bridgeport mill table. So this will form a pivot point for a fixture which will carry our rough casting. So what we have now is the stud, a 16mm bush which is a firm fit over the stud, and our T-nut in the T-slot. Now, fitting over that bush, we're going to attach a very heavy bar stock steel handle, say 75mm wide by about 12mm thick and at least a metre long. It'll have a 16mm pivot hole in the left hand end sitting on that bush. Next, we fit our bracket to this steel arm with a couple of screws or bolts. The important thing here is that the face we want to machine needs to be exactly 197 from the centre of our pivot. This will give us the correct radius after the machining is done. In order to hold that arm down, we're going to fit a Belleville or a spring washer and an M12 nut, and nut that down tight enough to make that joint firm. Now, to do the actual machining, you want to get a good long slot drill and place that adjacent to the face we want to machine, and then sweep the arm past the milling cutter, and that's going to give us the face now machined at the correct radius and square to the arm. Now, having said all of that, I'm not going to do it that way. This is the setup I used for machining the first casting. I was able to grip it in the vise there, and that was fine. With this one here, this face of the casting, or this leg of the casting, it's very slightly tapered across that face there, and now I'm out of cranking down on that hex key was going to get that to sit without pivoting. So I'll use this little angle plate, and I've got a toe clamp on this side. I've got a single M8 screw through from the back, and I'm pretty sure that's going to hold that securely enough. Let's hope anyway. Okay, this is just setting these two edges level at the back here where the casting is more or less symmetrical, and we'll lock that down and then we'll set our X and Y. Okay, here we go, probing this back face to get our Y. So that's set to 0. Okay, probing X. And that's set to 0. So we'll get our tool set up now and we'll set our Z. The tool I'm using here is a 2-flute 10mm ball nose end mill. In reality, setting the Z here is really not that critical. The radius will be the same no matter how deep I cut, and all of these features on the back of the bracket are pretty irrelevant really, within limits. So I'm just going to set this using the quill. Come over a bit more in X. So we'll lock that there and we'll set our Z. So I'm just going to go to our origin now, which should be this back right hand corner. Okay, I just sent that to X0, Y0, and that's the origin for our tool path. Okay, I can hear you sniggering already. You're probably saying, what is this? What is this low rent CAM product that you're using here? And why aren't you using something like Fusion 360 or Mastercam? Well, the simple answer is I've got Fusion 360, there it is there. I've got Autodesk Inventor, I use that a lot. But at the end of the day, this program, which is called CamBam, is simple and accessible, and I can get results out of this in a matter of minutes. If I do it on Fusion 360, it's a case of having sometimes too many choices. And although I've used it before and I've got successful tool paths, it just takes way longer than what I need for doing a simple machining operation. Remember, this machine that I've got is not a Haas Vertical Machining Center, it's not a Tormac, and it has fairly limited capability. So I don't need highly developed tool paths on this machine. So with this, I can create 2D drawings in, often I use Corel Draw, and I can then create pockets or profiles around those 2D shapes. In the case of a 3D object, I create that and import it as an STL file, and then depending on how you orient it, it will only create the tool path on the alignment of the Z axis. Now, you're also looking at this and saying, well, hang on, that looks nothing like the casting that you've got. And yes, I can import the STL file of the actual casting with all the machine faces on it, but it's a bit of a nightmare to orient it in this workspace. So what I've done is I've created this 2D shape here in the front, which has the correct radius on this upper surface here to match the Bridgeport mill, and the rest of the shape is really irrelevant, but I extruded that back to be the correct length or the correct Y direction of the casting, the way I've got it set up, and we've got the correct width in the X direction. The rest of that shape is irrelevant. It's just this concave surface on top that I need to look after. So the tool path that I've set up here is just a simple raster in the Y direction. It only cuts on the conventional milling pass, and then it just rapids back to the start. So yes, it takes longer, but remember, I'm not being paid by the hour here. This is just me doing my thing in the workshop, so I'm not bothered if I have to stand here and watch it rapid backwards and forwards. Okay, I've got this set up in Mach 3, and we're all ready to get going. So I'm just going to run this back to the start, and we might do a dry run first just to be sure that I haven't screwed anything up. I think I'm ready to run this now. I did have to lift the casting up a little bit, so I had some more clearance at the back where the cut comes off this edge of the casting here, and I needed to be sure I wasn't going to hit the angle plate. Now the first pass won't do much. It'll probably just clean up this little bit of a roughness in the center of the casting here, and then we're going to step down, say 1/2 millimeter at a time. And I know you're thinking, geez Mark, 1/2 millimeter, that's no depth of cut, is it? But remember, this is not a rigid machine, it's not a rigid spindle, the setup's a bit dodgy, so I'm prepared to take the time. Okay, here we go. Now that first pass wasn't very exciting, so I cut it short, but you can see how it's cut a uniform amount off the back edge of the casting, and this is what's going to produce that square face here to this back face. So naturally you'd expect it to be taking the stock off here. So I'm going to reset my Z and we'll do another pass. And by the way, this does two passes. It does one up from right to left and then comes back left to right, swapping directions, so it's still cutting conventionally. Alright, I'm calling that done. It's machined all the way out to this outside edge here, and I know you're looking at that and laughing and saying, mate, I could have filed it quicker than what you did there. And look, it's a case of understanding the limitations of this machine. I've tried taking deeper cuts and there was just too much chatter, too much vibration. Something was going to break if I went any deeper. So I did that in a series of shallow cuts and I got there in the end. And that's the important thing. Like, I don't have to make a profit on this, I'm just doing this for fun and a learning experience, and that is the first 3D tool part I've ever done. So I'm happy with that. Now I'm going to leave this fixed shed and I'm going to drill a pair of holes in this concave face here, and they will be to clamp this to the column of the Bridgeport mill. So there's my 1/4 inch through holes, and these need to be countersunk on the back, which is going to require a little bit of fiddling around to get that set up, but should be doable. But there you go, that's done. I want to use these 1/4x20 countersunk slotted screws to hold these brackets to the side of the Bridgeport column. So why go old school? Well, I've been told if you use metric fasteners on a Bridgeport mill, you can get drummed out of the Bridgeport Owners Society quick smart. So that's what we're going to go with, and I figure the easiest way to do this is to ensure that this is gripped to a 1, 2, 3 block with a clamp, and that should place these holes oriented vertically. So when the countersink goes in, it will form a true countersunk opening for the screw. Alright, so we should be able now just simply open these out for that screw head. Well, it turned out a bit ugly. Probably should have used a smaller countersink, but I don't have one with a long enough reach, and to get the depth that I need, we sort of cut into that fillet there, but that's okay. I'll fill that with a bit of epoxy and then we'll powder coat these later. That one's all good. Well, here's the question you've all been wondering about, but probably you're too polite to ask, but does it actually fit? And the answer is yes, it actually fits very nicely. However, let's see what happens when we connect both the brackets at the correct spacing. It's not such a happy ending. So these are the actual screws that I'll be using to hold the flat sheet material on top of these two brackets here. And there's a reason why I'll be using these. But that now has both the brackets at the correct center spacing according to my drawing that I created, and this radius in here should be the same radius as this section of the Bridgeport column, and that's roughly where it's going to go. Now with a bit of manipulating you can get both those arcs to fit against the circumference of the column, but as you can see it's not really a perfect fit. And remember I said that this section of the column here is just cast, it's not machined. It's got a certain amount of flare in that as well, and obviously that flare is different over on this side here. Now, I'm not sure how they get around this on the commercially made versions of this bracket assembly, but what I will be doing is using the same method I used when I fitted this work light bracket to the side of the ram. So in other words, I'll be putting an epoxy, metal filled epoxy on that surface there, and then we'll screw that hard against the side of the Bridgeport column, and that epoxy will conform to whatever shape we have here, and when it's all powder coated you'll never know it was done that way. So it's sort of a little bit bittersweet. I was hoping that that was going to be a much better fit, and that's all down to this discrepancy that we've got in this casting. Alrighty, on that bombshell, I think we're going to finish this video here now. When we reconvene, we're going to look at making the flat part of the collet rack. We're going to do all the shaping, drill all the holes, fit up all the accessories, and we'll powder coat this. And we're going to do that process of bonding the epoxy resin to this machine surface and getting it to conform to the shape of the Bridgeport column. Now, with this texture here, I sort of knew that's what I would have to do when I made this. So I wasn't worried about getting an aerospace grade finish on that casting there. I couldn't achieve that on my mill anyway, and there was no need. And it's going to help actually when we smear that with that epoxy. It's going to bond a lot better to that textured finish. So join me for the next video, and I hope you enjoyed this one. And yeah, Prezzo signing out. I'll catch you on the next one. Thanks for watching. I don't know, do you think they bought that? I think they did.